Hi guys, my name is Peter C. Dugba Jr., math instructor at the University of Liberia and your math tutor. And in my today's lecture, I will be looking at differential equations. In particularly, I'll be looking at separation of variables. So in previous lectures, we did a lot of problems on the separation of variables. So we want to continue solving more problems so that we all have better understanding on how we can solve just any problem involving separation of variable, or how we can test for separation of variables. Okay, so let's get started. Now the first problem, question 10, says dy by dx um, equals to xy plus x plus y, and then you have plus x plus 1. Now if you look at this problem carefully, so we look here carefully, we see that this term and this term, they are related in terms of having common factors. So we can group them. So we have xy plus y. We can group these two terms, and then we group x plus 1. So our first target is to ensure that we have set of factors where within those factors, every expression in there is in terms of a single variable. So you check in there, you have x and y. So we want to make it to be in terms of a single variable. So we have dy by dx equals, so if we factor out y, we have x plus 1 plus x plus 1. So we can cross multiply, right? So we cross multiply, meaning we multiply this dy by 1, and then this x dx by this entire numerator. Mind you, we can factor out something comma, this and this is common, so we bring it outside, x plus 1. And then what is left, if you take this expression out, you left with y plus x plus 1 going to x plus 1 is just 1 times. So dx, because we already cross multiply. So now since this is dx, we need only x expression here. So we must divide this out by y plus 1. Y plus 1. So you have dy now over y plus 1 equals x plus 1 dx. So because the variables now have been separated, we can integrate both sides. So the integral of dy by a linear expression, which is y plus 1, is just equal to the ln of that linear expression. Equals, the integral of x is just s squared, and the integral of 1 is x. This is s squared over 2, plus some arbitrary constant c. So now we want to solve for y. So what we could do, we could bring in a property that states that e raised to the ln of x is equal to x. So since we want to apply that property, we can say, let's say e ln of y plus 1 equals e raised to x squared over 2 plus x plus some arbitrary constant c. So e raised to ln of this expression is just equals to y plus 1, and then e raised to the ln, okay, let's take the, okay, so this is just equal to e raised to x squared over 2 plus x. Now we can take this constant portion from there, because we know that e raised to a plus b is equal to e raised to a times e raised to b. So if we consider this first two to be a, and then times e raised to c, so it's the same as saying e raised to x squared over 2 plus x plus c. Because if you're multiplying these two, since the bases are the same, you're going to add their powers. The reason why we separated c portion, because we just want to represent this entire e raised to c to some arbitrary constant, whether a, b, c, or whatever constant. So we want to solve for y now. We send this one across. We have e raised to the power. So e raised to the power c, we just rewrite it as c. So it will just be c times e raised to the power s squared over 2 plus x, and then minus 1. So this is our general solution for the first problem, question 10. Let's look at question 11. So question 11, the first thing we can do is to factor out what is common, y and y. So we got dy over dx. So we can bring out y, x plus 1 over, now x is common down, x, y plus 1. So we can cross multiply now, right? So we cross multiply is x, y plus 1 times dy equals y, x plus 1 times dx. So we need all expression here to be in x and all to be in y. So we can divide this out by x and by x. We don't need x and we also don't need y. So we say times y and then times y. So x and x will go out. Y and y will go out. You'll be left with y plus 1 over y dy equals, now this side now is just x plus 1 over x dx. So the variables now have been separated. We integrate both sides. So both of them are just similar. So we can say the integral of y over y dy plus the integral of 1 over y dy equals to the integral of x over x dx plus the integral of 1 over x dx. So we took the integral of each term. So this is just y over y is just 1. The integral of 1 is just y. So the integral of 1 over y is just ln of y. The integral of 1 over x over x, which is just 1, is just x. The integral of 1 over x is just ln of x plus some arbitrary constant c. So another person could say, okay, this is my solution. It's of no problem. That's the same thing. You don't have to bother yourself too much. This could be your solution. Or we could decide to say, let's group all of the ones with logarithmic. So we have y equals to x plus ln of x minus, because we send it one across, minus ln of y, and then plus. So this c, we can just rewrite it as ln of c, which is just the same as a constant. So we can bring in the property now. So we know the ln of a minus b, ln of a minus b, minus the ln of b is equal to the ln of a over b. And the ln of a plus ln of b is equal to the ln of ab. So we can try to bring in those properties. So the first two, now y equals to x plus, so this first, the first two, ln of x minus ln of y is equal to the ln of x all over y plus the ln of c. So y equals, so the ln of x of a plus ln of b is just equal to the ln of a times, so it's like this times this, so it's x over y times c. So you just have x equals to ln of cx all over y. So this is our general solution for the second differential equation. So thanks ever so much for watching. Please do not forget to subscribe and follow us. Hit our notification button so that you get updates on new uploads. Thank you. See you in our next lecture.